Okay, so let us start with slump test first. Can you guys see the screen? Is the screen visible and the audio?
Yes, sir.
Okay.
Yes, sir.
The ease with which one can work with concrete is called workability. This can be measured using a simple test called the slump test. Let me show you the procedure. Slump cone test is a simple and popular test extensively used at sites to assess the workability of the concrete mix. The test should be conducted at the commencement of the concreting operations or whenever the workability of the concrete changes. The apparatus for conducting the slump test essentially consists of a metallic mold in the form of a frustum of a cone with a base plate. A steel tamping rod of 16 mm diameter and 60 cm height is to be used for compacting. The internal surface of the mold should be thoroughly cleaned of moisture and any hardened concrete before commencing the test. The mold is placed on a smooth, horizontal, rigid and non-absorbent surface. It is then filled in 4 layers with the thickness of each layer being approximately 1/4 of the height of the mold. Each layer should be tamped 25 times evenly using the rounded end of the tamping rod such that strokes are uniformly distributed over the cross section. After the top layer is tamped, the concrete is leveled with a trowel so that the mold is filled exactly to the top. The mold is then removed by raising it gradually. The concrete will subside. This subsidence is known as slump. This operation shall be carried out without any jerks or vibrations and within a period of 2 minutes after completion of final tamping. The difference in level between the height of the mold and that of the highest point of the subsided concrete is measured. The subsidence measured is the slump of the concrete. The slump
I'm so sorry for the inconvenience. There's a bit of reconstruction happening in the department and they cut the power. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
I'll just play the video from the beginning again for even it will be helpful for those who joined late as well.
The ease with which one can work with concrete is called workability. This can be measured using a simple test called the slump test. Let me show you the procedure. Slump cone test is a simple and popular test extensively used at sites to assess the workability of the concrete mix. The test should be conducted at the commencement of the concreting operations or whenever the workability of the concrete changes. The apparatus for conducting the slump test essentially consists of a metallic mold in the form of a frustum of a cone with a base plate. A steel tamping rod of 16 mm diameter and 60 cm height is to be used for compacting. The internal surface of the mold should be thoroughly cleaned of moisture and any hardened concrete before commencing the test. The mold is placed on a smooth, horizontal, rigid and non-absorbent surface. It is then filled in 4 layers with the thickness of each layer being approximately 1/4 of the height of the mold. Each layer should be tamped 25 times evenly using the rounded end of the tamping rod such that strokes are uniformly distributed over the cross section. After the top layer is tamped, the concrete is leveled with a trowel so that the mold is filled exactly to the top. The mold is then removed by raising it gradually. The concrete will subside. This subsidence is known as slump. This operation shall be carried out without any jerks or vibrations and within a period of 2 minutes after completion of final tamping. The difference in level between the height of the mold and that of the highest point of the subsided concrete is measured. The subsidence measured is the slump of the concrete. The slump may either be a true slump, a shear slump, or a collapsible slump. The true slump is the desired form of slump that we require. In harsh mixes, the concrete slides down in an inclined plane. This is known as shear slump. In collapse slump, the concrete collapses as soon as the cone is removed. It usually occurs in very wet mixes. The concrete demonstrating a shear or collapse slump is considered unsatisfactory. In case of slump results beyond the specified limits, the mix proportion needs to be adjusted, especially the water content. The slump can also be varied by changing the proportion, size and combination of the various sizes of the aggregates. It is advisable to assess the workability of concrete mix using a slump cone. Ensure that the cone is filled in a proper manner as indicated. Notice the type of slump. Shear and collapse slump are undesirable. Adjust the slump to the desired value by changing the proportion.
Everyone saw the video. So what I'll try and do is I'll just pause the video at various instants and I'll try to explain some of the key points. See, slump test is very important in the sense, I told you when you start your mix design, okay, the various inputs that is required. For example, the grade of concrete, where the concrete is going to be used, the sort of exposure condition, meaning is it on the seaside, is it in a residential area, is it in a waterlogged area, okay. In addition to all this, workability is something that the client needs to mention. The client needs to tell us, I need 50 mm slump, I need 150 mm slump, I need 200 mm slump. So what do all these numbers indicate? I think you must have realized what these numbers indicate from the video and the end in the video. When you measure the this amount that you see measured in mm, okay, from the top of the mold to the highest point on the collapsed whatever this slump of concrete is. Okay, this is in mm. So in this particular case, if you notice this, in mm it is about 130 to 140 mm, 13 centimeters. So this concrete has a slump of 130 mm. Okay, this number that is there is what the client needs to specify. So why is this slump important? Now it depends on the purpose. Imagine the concrete that the client has ordered is to be used for, say, laying of the foundation. Okay, so foundation is typically, flat bed. It is not very deep, and it can be easily compacted with the help of, tamping or something else, pounding, for example. So in such cases, you might not really need concrete that is very workable. So in such case, the client might order, 50 mm slump is enough. Whereas suppose the client wants to cast a very deep column or a very deep shear wall, okay, where you can't really insert even a vibrating needle, or your rodding or tamping won't work. In such cases, what do you want? You want the concrete to flow easily. Okay, maybe in that case, the client will desire a slump of 200 mm, 250 mm. So he needs something that is more workable. So once this RMC plant delivers the concrete to the site, the first thing the site engineer will do is take a sample of concrete and do slump test. If the slump test passes whatever the client's requirement was, okay, he'll accept the concrete and it will be used for placing of concrete and concreting further. In case the mix was done beforehand, or if there is a delay in delivery and the slump is not as much as required, okay, suppose he had asked for 200 mm slump and he's getting only 50 mm. What does it mean? It is not as workable as desired, and there's no way for him to compact it effectively. So he has the right to reject the concrete, telling your concrete is not as workable as I wanted it. I do not want this. Okay, he is well within his rights to reject. Now, how does this test work? You have a frustum of a cone. Okay, so this is a frustum of a cone. So it has a height of 300 mm. The top diameter is 100 mm. The bottom diameter is 200 mm. So basically, whatever concrete you have, you fill it into this. Maybe one key difference between this video and the test that we'll be doing, or the procedure that is given in your lab manual, is here he says fill it in 4 layers. Okay, each layer tapped 24 times. We do it in 3 layers. Okay, 3 layers, 1/3, 1/3, 1/3. Each layer tapped 24 times. But effectively, we also do it in 4 layers because after the 3rd time we fill it and tamp it, little bit of the top concrete is come out. So in such case, we take some excess material, fill the top, make the level surface. But compaction, we do only 3 times. Each layer tamped 25 times. And the stamping is done using the stamping rod. Okay, the stamping rod I explained in the compaction part also. So this is a tamping rod. It has a diameter of 16 mm and it has a height of 60 centimeter. And one of its sides is a flat head and the other has a rounded head. Should always use the rounded head to do the compacting. And when you are doing the
Rod of
tamping
60
process,
millimeter
you should
diameter
ensure
and
that
60
you
centimeter
evenly
height
distribute
is
the
to be
tamps
used
throughout the top surface. You don't localize it to only one zone. So if you localize it to one zone, you'll get a shear failure of slump in the end. You should ensure that the compaction happens uniformly. Okay, and once you fill concrete in 3 layers and you finish the top level of the surface like this, when you're lifting the slump cone to the top, 2 key things to notice. You should never shake it too much. Okay, and you should never twist it too much. A slight shrug is fine, okay, to ensure that the concrete is not sticking to the mold, but you should never shake it too much or twist it too much. That will sort of not damage it. It will sort of disturb the concrete that is inside. Okay, and the results will not be very accurate. So that is one key thing. No shaking, no twisting. So in order to avoid the shaking and twisting, what we tend to do in the lab is we oil the insides of the slump cone and the bed. So we apply a greasy oil sort of a thing on the surface, so that the concrete, when it's poured inside and compacted, it does not stick. So when you try to lift the slump cone, it comes off very easily. So that one thing they're not doing it in this video. So we'll oil the thing and then lift it. And once we lift it, we need to measure. Okay, so this measuring thing can happen 2 ways. Like one, he's shown it in the video. What is he done in the video? He's inverted the slump cone, placed it next to the collapsed slump. Okay, and he measures the distance from the top of the slump cone to this thing. The other ways these days, all these slump cone comes with an attached limb here. Can you see this limb here? Okay, it is a hexagonal limb, or it sort of resembles an hexagon. What you can do is you can lift it, make sure it is vertically upright exactly above the slump. And there is a hole that is provided on top of this hexagon through which you can insert a scale or something to measure the value of slump that is measured. And one more key thing is, in this case, he used a slump scale to measure the slump. Okay, your scale is not always handy, especially in site conditions. So if you look at this stamping rod actually has graduations of every 10 mm. Okay, so in case you don't have a scale, you can use the stamping rod as well to measure the slump. So just keep that in mind.
Or vibrations.
That is as far as slump test is concerned. And like he told, there can be 3 types of slumps that is observed. One is a true slump. A true slump is when it is not flown away, it is not broken and fallen apart. The shape is retained, but the height is decreased. This is true slump, meaning your mix design is good. Your materials are holding together good. The paste and the aggregates form a good consistency together. They're holding together. Okay. Whereas when you go to the shear slump, what happens? The percentage of coarse aggregates in this case might be more. So what is happening? The paste that you've incorporated in a mix design might not be sufficient to hold the entire or bind the entire thing together. So what happens? There will be a shear failure, and shear failure normally happens in an inclined plane. Okay, you can notice this when you're filling or just playing with sand also. So if you make a heap of sand, beyond a certain point, what happens? There's a layer of thing that shears off. Okay, same concept here. So there is not enough force to hold them together. So if you notice a shear slump when you do your slump test, again, reject concrete because the mix design is not proper. The other type of slump that you can observe is a collapsible slump, where everything flows away. This can happen when the mix has too much water in it. Okay. So collapsible slump should not ever be mistaken with, say, self-compacting concrete. In self-compacting concrete, again, you will notice something like this, but the concrete will flow. But there, despite the concrete flowing, everything is still together. It is a viscous mass. In case of collapsible slump, that is not the case. Your aggregates and water is separated from the rest of the paste matrix, and it is just very, incohesive. So if you notice a collapsible slump when you do a slump test, again, reject the concrete sample that you've got. Clear? So again, this is how a shear slump looks like, and this is how a collapsible slump looks like. Is everyone clear with how to perform the slump test? So what are all the things you need? You need a slump cone, you need a tamping rod, okay, and a scale. That is all. If you don't have a scale, you can use a tamping rod to measure as well. So that is as far as the slump test is concerned. Everyone clear with slump test? Can we do the next test? We have half an hour. We will try and finish the other 2 tests. Clear?
Yes, sir. Yes, sir.
Okay. So moving on to the next test, that is VB test. I'll finish off VB because slump test is a part of VB test. I'll tell you how. Okay. Is the screen visible?
Yes, sir.
Consistometer test for concrete. VB consistometer test is used to determine the mobility and compactability of concrete. The VB consistometer test consists of a vibrator table resting upon elastic supports, a metal pot, a sheet metal cone open at both ends, and a graduated rod connected with glass disc. The entire setup is shown on the screen. For dimensions of the various shapes are designed based on the IS 11991959. Today, we are not going to concentrate on dimension. Let us now start with the procedure. Place the slump cone inside the cylinder. Now, fill the concrete in 4 layers. Each concrete is 1/4 of cone height, and tamper the surface 25 times. Once filled, struck off the excess concrete. Move the glass disc attached to the swivel arm and place it on the slump cone such that it touches the top of the concrete level. Note down the reading in the graduated rod. Next, remove the cylindrical cone by raising the cone slowly in the vertical direction. Again, place the glass disc and determine the reading. Now, switch on the electrical vibrator and at the same time switch on the stopwatch. The concrete will start to spread in the cylinder container. Continue the vibration until the concrete is remolded and the surface of the concrete becomes horizontal. Stop the vibration and stopwatch. The time in the stopwatch denotes the workability of concrete. The time is expressed in VB seconds. Calculations in VB consistometer. Initial reading in the graduated scale before remolding in. Final reading in the graduated scale after remolding in. Slump value is equal to a minus Pm. And the consistency of the concrete is measured in VB seconds. The workability conditions with respect to VB time are displayed on the screen. Thank you for watching. Stay tuned. The best is yet to come.
So did you guys see what happened? So the first part of the test is exactly like how you would do a, your slump test. So if you can see on your screen, I've quickly Googled an image of what a VB consistometer looks like. So you basically have a vibrating table. Okay, on the vibrating table, you have a cylindrical container. Okay, inside the cylindrical container, you place a slump cone. And to fill the materials inside the slump cone, you have this funnel that is there. And there is an extra attachment that is a limb that has a transparent glass disc that is there at the bottom. Okay, now how this entire thing works is, so the first part of the test is exactly similar to a slump test. You take concrete, fill it into this mold in 3 layers, tamp each layer 25 times. Okay, and then lift the cone and measure the slump. So this measure, how to measure the slump? Here they have this graduation on the rod. So you can place this glass disc on top once, and once you remove the cone, place the glass disc on top of that again and measure the distance. You get the slump. It is the way you measure might be different, but the slump that you'll get will be exactly identical to whatever you got in the previous process. Okay. The next part of the test is where it is tricky. So what you do is you remove this funnel from top, you remove this cone, this glass disc that you see, you rotate it and make sure it comes and sits on top of your slump, the true slump that is observed. Okay. So as soon as it touches there, what you'll notice is this is a transparent glass disc, correct? This transparent glass disc, wherever it touches the concrete, the cement paste will come in contact with the glass surface, and the transparent concrete will become that cement color, the paste color. Okay. Once that is done, get a stop clock and start the vibrating table. Okay. As soon as you start the vibrating table, what will happen? This bed that is there will start vibrating, and the concrete that is inside the cylindrical container, initially that was in the form of a frustum of a cone, will eventually, start compacting, vibrating, whatever, and take the shape of the container. When I say it will take the shape of the container, it will become exactly, its top surface will become exactly this round, the circular area. Okay, the key thing to notice here is this surface area of the cylindrical container, this opening, is more or less equal to this surface area of this glass disc. Okay, initially, when the glass plate was touching the concrete only in a few places, only a few spots on the glass disc was wet with your cement paste. But eventually, when the concrete is entirely compacted and taken the shape exactly of this container, this entire glass disc becomes wet with cement paste. Okay, so if you read all these manuals, they tell VB time is the time in seconds taken for the concrete to completely change shape from the frustum of a cone shape to the cylindrical shape. Okay, but it is very difficult to gauge with our naked eyes what that exact point is at which it becomes exactly cylindrical shape. So this glass disc will help us with that. Okay, as soon as you switch on the vibrating table, start your stop clock, As soon as you notice this entire glass disc has become wet. Okay, it is no longer transparent. It is entirely that cement paste color. Stop your clock. As soon as this entire thing has become wet, what does it mean? The concrete has taken the rectangular shape, and this thing is sitting comfortably on top of the surface. That is the only way this entire thing can be wet. Correct? So this time in seconds that you record between the start of the machine to this time this entire thing becomes wet is called VB time or VB consistometer time. So in the previous test, slump test, we were measuring the distance or the collapse slump in millimeters. Here we measure the consistency in seconds. So if you have a very harsh mix, okay, say a mix that has very low slump, 0 slump, 50 mm slump, obviously it will take more time, okay, to compact and make this entire thing wet. Okay, if you have a very high slump concrete, say about 200 or 150 mm slump, you might require less time. So you can sort of, form a correlation between slump test and VB test. So how does it work? If it has low slump, the VB time will be more. If it has high slump, the VB time will be less. So for things like self-compacting concrete, your VB time is going to be 0, because as soon as you lift the slump cone, it will eventually flow and occupy the shape of the container. You don't really need to switch on the vibrating table at all. Clear how the test is done?
Yes, sir.
I think whatever doubts that might exist will get cleared once we do the experiment in your lab. For now, just pay attention to whatever is happening. Okay, if everyone is clear, we can move on to the last test. Clear, everyone?
Yes, sir.
Okay, moving on to the last test. It is called compaction factor test. The screen is visible.
Compaction factor test for concrete. The compaction factor test is designed generally for use in the laboratory, sometimes used in sites. This test has an advantage of using this method for concrete mixes of very low workability. The compaction factor apparatus consists of the upper hopper of dimensions, top internal diameter 25.4 centimeters, bottom internal diameter 12.7 centimeters and internal height 27.9 centimeters. A fixed lower hopper of dimensions, top internal diameter 22.9 centimeters, bottom internal diameter 12.7 centimeters and internal height 22.9 centimeters. And a cylinder C of internal diameter 15.2 centimeters and internal height 30.5 centimeters. The distance between upper and lower hoppers and lower hopper and cylinder is 20.3 centimeters. Procedure. The sample of concrete to be tested is placed in the upper hopper up to the brim. The trap door is opened so that the concrete falls into the lower hopper. Then, the trapdoor of the lower hopper is opened and the concrete is allowed to fall into the cylinder. The excess concrete in the cylinder is leveled. The outside of the cylinder is wiped clean. Now, the cylinder filled with concrete is weighted. This weight is known as the weight of partially compacted concrete. Then, empty and clean the entire cylinder. Now, fill the cylinder with concrete in layers where each approximately is 5 centimeters deep. Once fully filled, the top surface is leveled off. The outside of cylinder is wiped. Now, weight the cylinder. This weight is known as the weight of fully compacted concrete. The compaction factor is equal to the ratio of the weight of partially compacted concrete with the weight of fully compacted concrete. With the help of compaction factor value, the degree of workability is calculated with the help of the table. Thank you for watching. Stay tuned. The best is yet to come. Kindly do like, share.
Okay, fair, clear what was happening. I'll try and show how the apparatus looks like again. So if you can see the screen, this is how a compaction factor apparatus looks like. Okay, you basically have two buckets, or what we call as hoppers. So a top hopper, which is slightly bigger in size, and a bottom middle hopper, and then a cylinder at the bottom. So in this test, what we're essentially trying to measure is the compactive energy that is required, okay, to compact concrete. How does it work? So first take concrete and simply place it into the top hopper, okay, without compacting, without tamping, nothing. Take a trowel, take a pan, take a concrete, place it inside the top hopper. So at the bottom of this top hopper, you have a latch, like a gate, a small shutter sort of a thing. You open the latch, the concrete that is there in the top hopper will fall off into the middle hopper. Okay, so this is step one. So in step one, what happens? Something that was totally uncompacted, when it is dropped from a certain height, it achieves a certain degree of compaction. Okay, so at this stage, it is said to be slightly compacted. Next, what you do, open the latch at the bottom of the middle hopper as well. Now what happens? The concrete that is there in the middle hopper will fall into the cylinder. Okay, once it has fallen into the cylinder, you take it out, level the top surface, okay, and go and measure the weight. There was one small mistake in the video. Initially, what you should have done is you should noted down the weight of the empty cylinder. Okay, so weight of the concrete inside the cylinder will be equal to weight of the cylinder plus concrete minus weight of the empty cylinder. That is going to be your numerator, not the weight of cylinder plus concrete. Okay, because your equation or your compaction factor definition is the weight of partially compacted concrete to weight of fully compacted concrete, not your weight of the cylinder. It will be erroneous. Okay, just keep this in mind. So before you perform this test, go measure the weight of the empty cylinder, and then at the end of step one, go and measure the weight of cylinder plus concrete, and whatever value you get, W2 minus W1 will give you weight of concrete at the end of this partially compacted stage. Now, why do we call it partially compacted? Because the way we filled concrete into the cylindrical container is not through any means of human compaction, meaning we have not used stamping rod, we have not used a vibrating table, nothing. We have simply let concrete free fall twice from one hopper into another, from the second hopper into the cylinder. Okay, so this is my partially compacted weight. Now keep it aside. This is going to be in my numerator. Next, what I do, I take the same cylinder and the same concrete. I empty out the concrete. I have a class. 5 minutes. Okay, take out the concrete. Okay, and then fill the same cylindrical mold in 3 layers. Okay, each layer time 25 times. So this is, this procedure is similar to your slump test that we did. So what we are basically assuming is when we fill the cylindrical mold in 3 layers, each layer time 25 times, you're basically ensuring that full compaction happens. Okay, 1 second. Okay, I'm so sorry, someone was here. What did I tell you? Where did I stop? The bottom layer, fill it in 3 layers, each layer time 25 times. Okay, so we are basically ensuring that it is in fully compacted state. And normally you'll observe whenever you do this test, in the fully compacted state, whenever you go and measure the weight, it will always be more than whatever the weight you get from the partially compacted state. Okay, so the ratio of this partially compacted state to a fully compacted state is what we call compaction factor. Some textbooks actually prefer to define it as density of concrete in partially compacted state to density of concrete and fully compacted state. Nothing wrong, equally correct. It's just that when we talk about density, what is density? It is weight per your volume. So volume of the cylinder is going to be constant, okay, for both the partially compacted and fully compacted state. So density is weight by volume divided by weight by volume of fully compacted concrete. Volume being same, you can cancel it out. It effectively reduces to weight by weight only. Okay, so you can follow either definition, either it as a ratio of weights of partial to fully or as ratio of densities of partially to fully. Both are perfectly fine. Understood why how this test is done. So what is the maximum possible value of compaction factor? Hello?
1, sir.
Correct, 1. So if you have a concrete that is very flowy or very workable, your partial density and full density is going, fully compacted density is going to be equal. Okay, so the maximum value of compaction factor that can be achieved is 1. So for very harsh mixes, where the compaction does not effectively happen through this, two-fall method, your value is going to be less. And for very workable mixes, it is going to be slightly better. So why is compaction factor test important? So for mixes which are very harsh, when you do your slump test, you get things like 0 slump, 5 mm slump, 10 mm slump, and that is not really an accurate measurement of workability in any way, or you can't really assess it in any way. Whereas compaction factor test, you can actually do something with it. You get an actual value. In fact, the code book that we use for mix design, which is called 10262, only the recent editions, say from 2009 onwards, they prescribed slump test as a test for workability. The previous editions, say the 1983 edition, okay, where our forefathers had used it, slump test was not very common. In those days, compaction factor test was actually a very common thing, and people, tend to use those values. So slump is a very recent discovery, mostly because people in the other countries have started using it as a norm. Clear how the 3 tests are done? Any doubts? Is everyone clear?
Yes, sir.
Okay.
Yes, sir.
So I'll finish off one small part. Now we understood that we have to mix concrete, place it into all these tests and do all these things. But the next ideal question is how much concrete to mix? Suppose you get these experiments in the test. Okay. Suppose in your practical exam they tell you go perform slump test on concrete in the ratio 1:2:4 or whatever. How much concrete should you mix? Should you mix 20 kgs? Should you mix 50 kgs? Okay. So you need to be very scientific about it. You cannot mix how much ever you want. 1 second, I'll just erase this off. Can you guys see the screen?
Yes, sir.
Okay, it should be a blank screen. So I'll show you volume calculations for one thing. Okay, and the same procedure is applicable for everything. So in case they ask you to cast 3 cubes, you should know what to do. In case they ask you to cast 2 cylinders, you should know what to do. I will do it for a slump cone. Okay, so we just discussed what is slump cone. So it is basically a frustum of a cone. Ignore my drawing skills, they're very bad. Okay, a frustum of a cone whose height is how much? 300 mm.
300 mm.
Correct. The top diameter is 100 mm and the bottom diameter is 200 mm.
200 mm.
Okay, how much concrete should I mix? So basically I need to mix concrete that will effectively fill this entire thing. Okay, so to fill this entire thing, I need to know the volume of this thing. How do you find out volume of frustum of a cone? What is the formula?
So 1/3 pi r square h.
That is for a cone. What about frustum of a cone?
One by 3 pi h into capital R square minus small r square.
No, something else. It's very close to that, but what? Think of it. Okay, it's actually this. Okay, it's pi h by 3 into r square plus rr, where capital R and small r are the bottom diameter and top diameter. Okay, Some people tend to use a very different thing. So what they do is they find out the top area, okay? They find out the bottom area, they find out the average of these two, and they multiply it with the height. This is actually wrong, okay? If someone tells you to use this formula, please tell them, sir, this is wrong. We will use the correct method and use this formula. So it's pi h by 3 into r square plus rr. Now someone quickly take out a calculator and tell me what this value will be. So capital R is your bottom diameter, okay? So bottom diameter is bottom radius. So bottom diameter is 200 mm. So 200 mm, what will your radius be? 100 mm. 100 mm is how much? 0.1 meter. Is that correct? So substitute everything in meter. Okay, next take your top. So it will be 0.05 meter. Is that correct? And the h is going to be how much? 0.3 meter. So substitute this and get me the volume of the frustum of a cone. Someone quickly grab a calculator and tell me the value. Done? Anyone finish? Okay, guys are very slow. I vaguely remember.
0.0055.
Okay, I vaguely remember the value. It should approximately be 5.5 into 10 power minus 3 meter cube. Is this correct?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, it's correct.
This is the volume of frustum of a cone in meter cube. Okay, next what you need to do, you have the volume. Okay, but you still don't know in what proportion you need to do the mixes. Correct. So remember this this thumb rule. So we assume the density of concrete rho should always be 2400 kg per meter cube. Okay, meaning if I have a cube, okay, if I have a cube and say this volume of this meter cube, volume of this cube is 1 meter cube, and I filled it entirely with concrete, and I went and measured the weight, it is going to weigh 2400 kgs. Okay, so this is always a standard. So this is something that you guys need to know. So if volume of this frustum of my cone is going to be so much, how much is the weight going to be? What is weight equal to? What is density? Weight by volume, correct? So what is volume equal to?
Density into weight.
Do this. How much do you get weight as?
13.18 kgs.
13.18
kg.
So what we'll do is, because you guys are still kids and you guys tend to play around a lot, we'll always assume 15% wastage. Okay. So whatever total dry weight we get in the end, multiply it by 1.15, meaning add 15% wastage to it. What do you get at the end of it? Tell me a number.
Sir, 15.1570.
Okay, let's round it off even further and tell we've got 16 kgs. So 16 kgs is the total dry weight of materials that I need to mix to comfortably perform a slump test. Okay. So next question would be 16 kgs is fine, but how much of what should I take? So in the question, say in the exam or test or wherever, they'll tell you perform a slump test on concrete mix of ratio say 1:2:3. Okay, with a water cement ratio of 0.5. Okay, now this water cement ratio of 0.5, keep it aside. This 1:2:3 you take. 1 + 2 + 3 is how much? 6. Okay, so this is basically a cement. This is your fine aggregate. This is your coarse aggregate. Now take a cement. So cement content will basically be this 1 divided by this total proportion 6 into this total dry weight that is there 16. How much is this? How much is this?
2.6.
2.661.
Correct. So next your fine aggregate will be 2 divided by 6 into 16. How much is this?
5.3.
Correct. The last thing is your coarse aggregate. So that will be 3 by 6 into 16. How much is this?
8.
When I add all this, how much will I get? Okay.
10.99. 16. 10 point.
You should get 16.
15 point. Yeah, 15.99.
Okay. So this total dry weight, okay, basically the sum of all the individual materials should be equal to whatever the initial dry mass that you had calculated. Okay. So to perform a slump test for concrete in the ratio 1:2:3, I need to take 2.66 kgs of cement, 5.33 kgs of fine aggregate, 8 kgs of coarse aggregate. Do a dry mix. Next, how much water should I add? I've told you water cement ratio is 0.5. So W by C is 0.5. And cement I know 2.66. So to get water, what do I do? I simply cross multiply 0.5 into 2.66. How much is this?
1.33.
Correct. So add 1.33 kgs of water or 1.33 liters of water to this entire dry mix. Whatever mix of concrete you get in the end, perform the slump test on that. Understood the procedure? So the only thing that might differ is your volume calculation. Okay, in this case, I've asked you to do slump test. In case I asked you to do something else, say compaction factor test, you'll have to find out volume for that. If I ask you to cast 2 cubes of 150 mm size, find out volume of cubes, multiply with density, find out weight, divide the weights in whatever this proportion is given. Okay, only the first step will differ depending on what test or experiment I'm asking you to perform. The rest of the steps will be the same. This is a standard. Okay, 2400 kg per meter cube is the assumed density of concrete. Understood?
Yes, sir.
Okay. With that, I think we've reached the end of time also. We'll stop here today.